I'd like to welcome you to the Woodrow Wilson Center. My name's Dave Rajewski, and I direct the Science and Technology Innovation Program. And I'd like to welcome you to the first post-election public discussion on geoengineering. It may be the first post-election discussion on climate change. If those of you who have been following the debates, there's been something that's, I think, been obviously absent on the side of both candidates. So I just wanted to just set some context before we start. If we went back a year or so, some of you might remember there were three major reports that were released on geoengineering. There was one by the Bipartisan Policy Center, and then right after that, the GAO released this report on climate engineering. And then we released a report that was done by Bob Olson on geoengineering for decision makers. That was actually 1 year ago. And when we released this report, we actually had the GAO and the Bipartisan Policy Center here to sort of talk about all three of these and what they were presenting in terms of recommendations. Then things sort of disappeared in terms of discussion. And I think, it's interesting that geoengineering is now back on the screen. Some of you might have seen the Naomi Klein piece in the op-ed. It was focused on someone dumping 120 tons of iron particles in the ocean. And there was also a piece in the Washington Post in the Health and Science and Tech section, I think last week, on geoengineering. So obviously it's beginning to appear on people's radar screens. I think the most dangerous thing about geoengineering may be a lack of discussion about it. I think we get into real problems if we stop talking about it. So I think one of the things we really want to try to do here is to relaunch the discussion. And I think what we did was we went back to Bob Olson about 7 months ago and said, could we come up with some new idea, some new take on geoengineering? And Bob thought about it a little bit, and we thought about it, and came up with this idea of what we're calling soft geoengineering. I'm not sure that's the best term for it. We'll have a debate about that, I'm sure. But the idea was, could we actually, are there technologies out there which would allow us to make interventions that would provide multiple benefits, would be reversible, that could be scaled up, scaled back if there are problems? This is probably a good set of solutions if we're dealing with emerging techs in general. But it probably would be absolutely necessary with geoengineering. So we worked on that. Bob put together an article that came out in Environment Magazine. I think we've got copies out there called Soft Geoengineering that goes through some of the principles and also highlights a number of technologies we think essentially meet the criteria that Bob laid out. So what we've done today is we've brought Bob back to go through those. And we have two people that are actually working on the technology. So you'll get a chance to have a much deeper dive into what these technologies are and how they work, what the economics might be, scale up issues and whatnot. And then we have Jim here from the ETC group to sort of provide a response, counterweight, whatever it is going to be, we'll see, in terms of possible issues around NGO. So we'll start with Bob Olson. Bob, you should have bios for everybody, by the way. Bob's a senior fellow at the Institute for Alternative Futures, spent lots of time doing technology assessment. Worked at the old, now defunct Office of Technology Assessment. Leslie Fields, he is here from California. Leslie is a consulting professor at Stanford now, but has been in and out of universities and businesses, both large and small, for a number of years. Russell Seitz has come down from Boston. Russell's been in and out of, again, academic institutions, Harvard, MIT, and also is working on his own sort of small company now. And Jim Thomas is here from the ETC group, and Jim directs the research program. So what we're going to do is kind of go down the row, I think. We'll start with Bob, sort of looking sort of generally at what is this concept of soft geoengineering, and then we'll go through the technology examples and then have Jim provide some comments, and then hopefully we'll have some time to open it up for Q&As. So with that, I'll start. We are videotaping this, so it's by default on the record. We'll put the video up online. It's not going out live, but we'll put the video up online in a day or two. And you'll also be able to access the slides. And we'll also have a list of all the participants that are here, in case you're wondering who else is in the room. And you'll get a sense of that, hopefully, as we do Q&As. So I'll turn it over to Bob, and we'll get going.
Okay. For any of you who haven't become familiar at all with the concept of geoengineering, here's the quick definition that we had in the Geoengineering for Decision Makers report. Intentional interventions in the oceans, in the atmosphere, oceans, soils, or living systems to cool the earth in order to counterbalance the unintentional interventions we've been making that are heating the earth. It's a very bold concept to talk about cooling the earth. Until a few years ago, it really wasn't taken seriously. The situation has changed, and I think these are the main factors that climate change is occurring faster than climate models even anticipated. Many climate scientists are worried that it could come to a point where our interventions in nature begin to provoke self-accelerating changes in nature itself. Leslie will talk more about that, where climate change might really accelerate in a way that we couldn't do anything about. So while this is going on, the international efforts to regulate emissions have not been very successful at all. As Dave just mentioned, the political situation in the United States has just been paralyzed on climate change. And it's because of this situation that more and more scientists are saying we've got to look at geoengineering. In the past, people have been reluctant to do it, but more and more people are saying we need to take a look. But that's also then leading to some scientists and some environmentalists really taking an oppositional stance, saying it's too dangerous, there's too many uncertainties, it could make a bad situation worse. So it's becoming a very active field of discussion now. I was, in doing that report that Dave held up, very concerned about the effects of many of the geoengineering technologies, particularly the one that's talked about the most, putting aerosol particles into the stratosphere to reflect away sunlight. And so I was asking myself, as Dave said, are there any approaches that are better, that are safer? And sat down with Dave and with Aaron, some folks here at the center, and came up with essentially my wish list of what I would like a geoengineering technology to be like if we had to have a geoengineering technology. Instead of going into the stratosphere with particles that affect the whole planet, it would be better if you could have something that was local, that was small, but that could be studied, and if it didn't seem to pose problems and if it seemed to work, you could scale it up over time, scale it up more, evaluate it. If it did seem to pose problems, you could it could be easily reversible. Ideally, it would actually have multiple benefits. It wouldn't just deal with climate change. It would have other good effects, and so forth. It had to be economic. It had to work. So came up with this list, and then I asked myself, is there anything that could meet all these or even the majority of these criteria? And went out with that question in mind, looking around, and decided that maybe there are. The first one is the one that Leslie is going to talk about, the ICE 911 concept. So I'll just be very brief, because Leslie will talk about it in detail. But her basis is that stopping the melting of the ice is probably the most fundamental thing we have to do. Because if the ice melts, that's the main thing that can trigger these self-amplifying processes. So she's been working with different kinds of covering materials in different shapes, different compositions that you could use to protect ice, or maybe even help new ice form. And it has to have very specific characteristics. It has to be easy to deploy and floatable and resistant to be blown away by the wind and easily removable. So she's been testing a bunch of these things. She's been doing it for 4 years. The picture on the top there is a material that she's working with this season. And below is a picture of Leslie out on the ice, where we actually grabbed her to come to this meeting. We brought her indoors to talk to us from just having been out working on the ice. So that's one concept. Another concept that may seem kind of goofy at first, but I find one of the very most interesting ones is Russell Seitz, who's also here, concept of bright water. You may have noticed when you're going over waterfalls in your kayak that the water around you is bright. Dark, deep ocean water is very dark. It absorbs heat like black asphalt. But water that has air bubbles in it is brighter. And Russell's approach here is that if you generate very small micron-sized bubbles, they're extremely bright. They're like little mirrors. And they also have a very slow rise time in water. They hang as a suspension in water. So that if you could generate micro bubbles, clouds, that it could be a reflective geoengineering technique. And it can be very powerful. His argument is that you could brighten one fairly large pond and it would have the equivalent effect to putting on 10,000 white roofs, and you could do it for about the cost of one roof. So how could you use this sort of thing? Well, a couple examples. You could have ships that were leaving microbubble wakes going around the edges of Greenland, cooling the water right around Greenland, creating an insulating kilometer or so of water so that even as Arctic water heats more, you'd protect the water right around Greenland from heating that much and perhaps be able to retard the melting of Greenland ice and sea level rise. A much more ambitious example for later in the century might be that there are thousands of naval and commercial ships that are always plying the world's oceans. If they could be leaving microbubble wakes that were then scattered by ocean currents, you could increase the reflectivity of fairly large amounts of water. Russell will really make this case that there are other uses for it that are perhaps the best selling points. We lose enormous amounts of water in our water storage and reservoirs from evaporation. And microbubbles could really slow down that kind of water loss. It could be used in something like Galveston Bay or Chesapeake Bay, with bubbles being generated at the sunnier parts of the day that would actually affect the microclimate and make the urban areas, Baltimore and Galveston, cooler and reduce air conditioning costs. So lots of potential benefits. And this is a good one to talk about the possibility not just of environmental problems, but of environmental advantages. If you can have more water in your reservoirs, you can extend the dry season water supply. If you do this in rivers, you can increase the amount of water in rivers and river flow, which can help conserve wetland habitats, and so forth down this list. I don't want to go through it all. But also note that this and all the things we're talking about avoid some of the risks of other geoengineering techniques like affecting the ozone layer or turning the sky white, which aerosols would do. It even results in a net reduction of atmospheric CO2 because cooler water absorbs more carbon dioxide. Another concept is that a number of people, including our Energy Secretary Chu, have recommended is to have our built environments, our roofs, our roads, our building structures lighter to reflect more light. Hashim Akbari in Canada did a quantitative analysis here where he studied images of the Earth from space and estimated that this kind of whitening of roofs and pavements and buildings could make urban areas more reflective by about 10%. And he, using satellite data on the extent of cities and climate models, he made estimates of how much that could cool the climate. It turns out it's not very much. It's not enough to justify the costs of doing all that. But he estimated that doing this would, especially in warmer areas, make for a major reduction in air conditioning costs. That goes up into the realm of $50 to $100 billion a year saved in air conditioning costs. And it also makes outdoor environments more comfortable, which is what traditional architecture, like this image of Santorini in Greece, they weren't trying to cool the climate. They were just trying to cool themselves by having reflective structures, so it would do that. So it doesn't make sense just for affecting climate, but some effect on climate comes as a bonus for big energy savings. Another concept is to actually take carbon dioxide out of the air, capture it out of ambient air. The technology to do this has been around for ages. Submarines have done it for 75 years. But everybody who's looked at this in the past has said, oh, this is just much too expensive to do on a large scale that would affect the amount of carbon dioxide in the atmosphere. But over the past few years, at least 4 startup companies have come into existence that are betting that they can do it. One of them was founded by David Keith, the climate scientist at Harvard, called Geoengineering, and this is a picture of the kind of device that they're aiming to create. They've already created one little section of this and are testing this prototype. But what they think they could do that would make it economically feasible is you just don't talk about sequestering the carbon dioxide. You think of it as something that's a commercially valuable product, something that you could sell and make money on. Oil companies use carbon dioxide for enhanced oil recovery. You take liquid carbon dioxide and you pump it down into wells that look like they're dry, but actually have a lot of what they call stranded oil still in them. And as the liquid carbon dioxide evaporates, it creates pressure that lets them get more oil out. So their line of thought is if we could get the price down to $200 a ton, we could start selling this by the tons to oil companies, and as we ramped up production, we would get better and better at doing it, and our costs would come down, and then we could start using it for other things, like producing algae-based biofuels, which require a lot of carbon dioxide, and that you might be able to move toward a fuel system where you take the carbon dioxide out of the air, you make biofuels with it, you burn the biofuels, it puts the carbon dioxide back into the air, you take it out of the air, in other words, a carbon-neutral fuel system. And one last one, the very imaginative and brilliant physicist Freeman Dyson, in a book a couple years ago, just almost as an aside, talked about the concept that you might be able to store vast amounts of carbon in the soil. There's a limited amount of carbon that exists in all the plants and plant materials on the Earth, but he thinks that there really probably isn't any practical limits to the amount that you could store in the soil. And to do that, you'd have to increase soil biomass by a certain amount per year, and he thinks that you can do that by shifting to no-till farming so that root material doesn't get stirred up to the top and decay up there. It stays in the soil and forms biomass in the soil as it decays. You could also breed plants to have larger root systems. You could make more use of cover crops, a good organic farming technique that has more plant material growing all around the year. With all of these, I'm not quite sure what to make of them, but it's an interesting idea. Not his idea, but other people have talked about the use of biochar as a soil amendment. Biochar is basically a fancy name for charcoal, but it's a form of carbon that won't break down, and it's actually, up to a point at least, it's actually good for the soil, a good soil amendment. So that's one more concept. So this is taking a look at how do these different ideas rate as by the criteria that I set up in the first place, and it's not quantitative, it's just a judgmental assessment. And there's enough yeses there to make me fairly optimistic that these are worth more attention. I'm not saying we should do these things, I'm just saying these are things that have been under the radar, not given enough attention, and deserve some more attention and study. There are some things here that are definite no's, like you can't reverse built infrastructure or soil that you've made, but I don't think those are significant things. I've got question marks about the cost effectiveness of many of these things. And on the low negative impacts, I've got yeses for use on a fairly small and local scale, but asterisks saying, to the extent you scale up, you've got to keep looking to see if problems emerge. You can't assume that something is going to be, as safe on a larger scale as it was on a smaller scale. So one last thought that I'm sure we're going to come back to many times here is the importance of governance for the development of geoengineering. Dave just mentioned this guy who's pictured here who dumped 100 tons of iron oxide in the ocean off British Columbia without approval from anybody, in violation of various international treaties. Rogue geoengineering. You can also imagine rogue geoengineering coming from countries. You imagine India is, wells are going dry, rivers are going dry, people are starving. International situation is, in terms of approving anything, is just clogged, and the country just deciding to go ahead because it feels so desperate. Another kind of rogue behavior. So we got to head that off. We need a legitimate process for managing the risks of research, and then on to, research that involves smaller deployments and perhaps larger deployments. It's really got to be worked out in a way that's legitimate. And the key point I want to make here about the technologies we've been talking about is that they just seem to me to be in a different category from global impacts geoengineering, like putting aerosols into the stratosphere. If people who are opposed to that kind of geoengineering make a blanket dismissal of geoengineering, including things like the ICE 911 and bright water, I think that could keep those things from going forward that might be very valuable to go forward. And it's the same for the governance processes. If Leslie, who is doing her work on a completely voluntary basis between teaching and research and other business activities, is forced to go through the same regulatory hoops to do a little field test that you have to go through to do stratospheric aerosols, it's just never going to happen. So I think a distinction has to be made between these small-scale, local kinds of approaches and the larger geoengineering approaches. Amen. Leslie, you're on.
Okay, so I should sit here.
Come on over here.
Come on over
Yeah.
there. Okay. Let me just gather my stuff. Great. Thank you. I really appreciate what Bob is doing, and I appreciate your taking the time to be here. I think this is an extremely important conversation. Let me make sure I understand this thing. Yes, okay. It might help you to know a little more of my background. In and out of teaching and in and out of various small businesses. Sounds actually kind of flaky. So pardon me, and I'll take a minute or two. I've got bachelor's and master's in chemical engineering from MIT back in the day. I've got a master's and a PhD from UC Berkeley in electrical engineering, specializing in MEMS. And I've been almost 2 decades between them working in large corporate R&D. I love research. Chevron Research, and working on catalysis to try to use fuels more efficiently, use oil more efficiently, and HP Labs, and a nice decade there. For the last decade, I've been a consultant, a technical consultant. Started up small business to do technical consulting. I've had lots of clients, and in honor of balancing things. On the side, for the last 6 years, I've come to what you see here, the relevant info here on what on earth am I doing in climate. I I saw the Gore movie, and I said, oh heavens, I think maybe there's something I can do with the gift of a very nice engineering background and a wish to create things. So I've founded this environmental nonprofit. As Bob said, it's all volunteer at this point, ICE 911. And I've been, at the same time, a consulting professor at Stanford, where I work with the people in MEMS a little bit, but mostly my main activity at Stanford is, these days, is I teach a class in engineering and climate change, so that mainly grad student engineers have a chance to come in and see what are various avenues that are useful for them to do research in to help the climate situation intelligently. And so we have guest speakers, among other things, in solar and electric vehicles and things like that, so they get a survey. So that's where I'm coming from. One of the things that provoked and alarms me, and it sounds like I should be making a case for geoengineering of some sort, or why we're concerned here, is this graphic. I haven't checked into it for a bit, but a couple years ago, MIT had this alarming graphic of the greenhouse gamble. And the point on this is basically, this is where their pie chart was when I started my work. Is it okay to, oh, I'm getting away from the mic, aren't I? Think of this, though, as a wheel of fortune just spinning around, you know, and where does it stop? The larger the probability wedges are here, those different colored wedges, the more the probability you'll end up there. And so in the day, when I started about 6 years ago worrying a lot about climate, their chart was on the left. And there was a pretty good chance we were only going to have 2.5 degrees C temperature rise globally if no big policies were implemented and adhered to. But within the last couple of years, they have revised that, and it looks far more dire. And so this is one motivation, is just the thought that what the climate scientists are saying is things could get pretty bad indeed. And what does that mean to us? Well, here's a lovely chart. I really like this. It communicates well. If you've got it available to you, it's worth studying. It's from the IPCC fourth assessment report, and Terry Root, Professor Terry Root, with a wonderful graphic artist, put together a summary, not as dry as trying to wade through the report, right? A wonderful summary of why do we care if the temperature rises? And we care a lot. And the two that I've highlighted here in black with this, you know, the bolding, is what the risk of extinction is of various species. So as Bob said, there's some point at which we can't go back. When I looked at that, you know, what goes through my head is, what kind of world are we leaving? And so would like very much to see if there's a way to slow this down, to buy us time. While people are doing all the things I get to teach in my engineering and climate change class, all the things you're probably working on of trying to make safer, better, you know, lower carbon footprint technologies. And so we have choices at this point. We can do mitigation, all those things we should be doing at full speed. Even if some geoengineering process comes along, we should be doing this full speed, because this is what we need to do, is make less of an impact. We should also be adapting. Apparently, New York City is in the midst of realizing that pretty full scale. What happens when sea levels rise? And maybe we should look at geoengineering. And believe me, when I started worrying about this project and deciding that I wanted to try to do something that made a difference, that moral hazard argument was very key in me. I've been under the radar to start with because I almost didn't even want to know I was thinking about this. It's kind of morally repugnant, isn't it? And yet, I think we might need it. And so my rules were, maybe we need to make it in all the ways that Bob has been talking about. We are so on the same page with that, of if you're going to muck with climate, then make sure you can undo what you're doing. It's a second choice, but maybe it's the one we need. So the motivation here again is conservation changes to the energy mix are needed, but they're too slow. It looks like, and it's going to be decades to substantially reduce even the rate of addition of CO2 to the atmosphere. So it isn't like we've stopped now and are taking the 2 degrees C that I guess we're already committed to. It's that it's still getting worse. So geoengineering, as you know, part of what's great about it, part of what's terrifying about it, is the solutions can be rapid. Some of the solutions, like the stratospheric sulfate aerosol injection, can be possibly irreversible, right? It'll be up there for a while. And if you stop doing it, my understanding from Ken Caldera is, if you go through a few years squirting these particles in, if you stop doing it, the return to where you would have been climate-wise is sudden. It's faster than it would have been in the first place. And so you end up with actually a faster pressure on species. You will probably have more extinctions and more sudden sea level shifts and things. So it's really, to me, I'm not an expert in that, but at least looking at that, I am terrified by that. And so what I've been working on, and got really some benefit of some nice mentoring early on, say, from Steve Schneider and Terry Root, very expert in this, Steve Schneider, unfortunately deceased, but was to, he dubbed this eco-engineering. He said, you know, this is exciting because it's the same reason Bob has come up with soft geoengineering. It's like geoengineering, but it's trying to do it with some humility. And so the boundary conditions I thought were absolutely necessary were first, do no harm. Make it reversible, make it removable, as small and local an ecological impact as possible. Because when you're going global, are our atmospheric models that good? When you're going local and you're just trying to rebuild some natural processes, perhaps you have a little less hazard there. And so this presentation, this little speech is just trying to show you something that's attempting to be a practical engineering solution to help slow the melt of snow and ice, possibly rebuild it. You can also use this for cooling water. I've established some of the materials in very small tests. You know, that's one good criteria to make sure you're building something that will make things cooler rather than building a pool cover and making things warmer. And trying to do this locally and see if it's a useful tool to slow climate change, focusing on the polar ice. And why the polar ice? Why does it matter? Well, there's an effect called the ice albedo feedback effect. The polar ice melt is in a positive feedback. I've had the pleasure through this project getting to talk with several really terrific polar and glacial ice experts over time. And they know, the ones who've been studying for decades know that the slope has been increasing of our ice loss. And the reason is, if you go around this little graphic, you're melting the ice more. Oh, you've got more open ocean area. Oh, that absorbs the solar energy better than the ice did. Ah, my ocean temperature went up, so you've got an increasingly warm bathtub. And the experts estimate that this one effect increases the global rate of warming by about 20%. And there are a lot of subsidiary ramifications that come from melting the ice. You're changing the currents. If you're doing it enough, you're changing the thermal and saline patterns that are then changing where the Gulf Stream goes. You're suddenly making winters a lot colder in northern European ports, but you're changing rainfall patterns. It's actually a big, big deal. And so that looked like a good thing to try to interrupt. And given my background, I said, maybe that's a material problem. And so maybe we should be making these floatable, removable ice caps. Here's a little bit more of why do we care. And this, I'm afraid I have to get up again, but this chart was the summary of what the IPCC concluded some years ago of what the ice melt was likely to be. And as you can see, you know, a lot of expertise. There's a lot of range of possibilities. What will it be? And of course you have to measure not over a year, but you're measuring summer to summer ice loss. Because you always have a substantial refreeze in the winter, which is an issue we'll get into. And so there was the average. But what happened in 2007 was this. And to my ice experts, that change in slope is actually no surprise. This year was pretty terrible, too. I haven't updated the slide. But, you know, one year's phenomenon is just weather. But when you have an increase in slope like this, it's a problem. So why do we care? Well, we talked about some of those far-reaching effects. We also have hundreds of millions to a billion people depending for their drinking water on glaciers, such as in the Himalayas. That's a big deal, as you were painting the picture. And finally, when we have ice sheets melt and ice start plopping into the ocean, once ice that has been on land is in the ocean, we get another source of sea level rise. A lot of the sea level rise we have now is simply thermal expansion as the oceans are getting warmer. That's a lot of what's driving it. But when you have ice actually melt, come into the ocean, you're raising sea levels. So it's a big deal. So what am I trying to do? This is a horribly complicated slide, but there's just a couple simple things. Energy comes in, it gets reflected by the surface, whatever the surface is, land or sea, it gets absorbed. I'm trying to change things here a bit, so put something that'll reflect more. And we have a water cycle going on as well. I'm trying not to turn into a pool cover, so I'm trying not to suppress evaporation. So we've got that. And then we've got everything that's going on here, interacting with the greenhouse gases that are in the atmosphere. That's all I really want you to get out of it, is we're trying to put some materials, just some local surface materials, to try to change that a bit. So here we are. Enhance the ice retention with floating removable materials is the thought. And the idea is that we could reverse it if we overcompensate, because people have been wrong about things before. Human beings do that. Our very long-term view is just, a microsecond in the history of this planet. And so what if this is a huge thermal excursion right now on our way to the next ice age, right? What if? We would want to be able to undo this if we mess up. And so that's one of the big wishes here. And we could also have, so I'm saying that we can put this adjacent to ice in the ocean. Here's our little raft here of stuff, floating stuff, and I'll get into what on earth that is. But in addition, one very nice way to protect glaciers and possibly permafrost is to put these materials up on, say, the meltwater on a glacier, trying to reduce that large collection of water that eventually gets so heavy that it flows down, it cracks underneath, and lubricates the slide of ice sheets off the glaciers. You can also put these, of course, on surfaces of snow and ice, and I do that a lot to test and see whether these are working, and it could be useful for permafrost covering as well. And the cost isn't outrageous if we take the most optimistic case for just the basic material, but we'll get into that in a minute too. So why do I think this is important? Well, for those who are engineers out there, this is kind of a classic way of looking at a control system. Let's say that red line is the uncontrolled line of temperature or CO2, whatever you want to call it. Just look at it, it's increasing. We want to do something about it. Let's look at the black line. We have deployed something. We have caused a nuclear winter. We have been wrong about where climate was going. We're in the next ice age. The planet's going to be fine, but we won't. So maybe we want to instead have something that we can tune. And so I have said before, I guess I'm saying for the record, I would die a happy woman if we get to, hopefully many years from now, if we get to the point where what we're arguing about is where that set point of just right is. Oh, it should have been the 1970 set point. No, it should have been the 2021, right? If we could go into things in a way that we think that we can correct what we're doing, so that we don't just put it out there and say, I know it's right, I know it's perfect, that's it, I'm done. No, I'm sure whatever we do, if we get on a scale like we're talking about, we have to be able to control it both ways. So what have I been working with? I've been working with several materials, and here are pictures of some deployments we've had. I started out really small scale in hula hoops. They float for a while. Have gone to largish sheets, and have gone to some biodegradable modular materials, and have gone to low-cost floating glass. Everything I do in field testing has either been, well, on our deck, that's easy, I can do things in tanks, or on a lake up in the Sierra where they have been, in the Sierra Nevada mountains of California, where they have been very, very kind, the water district and the homeowners, about giving us permission to work there. And everything I put out there, I have to make sure I will leave no trace. And so you will see everything is very contained, and we spend a great deal of time pulling things back. What is the stuff I'm talking about? What is in that bag on the bottom? It's a form of floatable hollow glass. It's got a lot of pore structure in it, and it floats. And is it okay to pass it around?
Sure.
Yeah.
Don't drink it.
Don't drink it. I've mixed two sizes here of just stuff that I have. It's basically, as you're questing for a material, I thought, well, floating sand is about as non-toxic as you can get. And so that is the material we're looking at now. We've gone through a number of tests. It's work ongoing. And we just, as Bob said, put out a deployment on Monday. But, it's real life. When you're doing this, it doesn't ever go as planned. And it's certainly not secret. Everybody who lives up there comes by. The water district is helping us out there. And I hope you guys can still hear me when I do this. I went through, after I got things assembled in the bags, just squirting them like crazy to make sure the basic, these materials as formed are a little bit basic. I didn't want to dump a lot of base in their lake. It turns out, however, that they spend a lot of time in their pump house neutralizing acid in their lake, and what I've been rinsing out of these are what they add in. Here's a water engineer who helps us a lot. It's like, oh. But that's the level of caution that we work with. Here's the back of the car where I was doing some final assembly, the lake. This time we're trying to hit it before the freeze. We want to see what happens to these materials before the freeze. Here's one of our team assembling. There's me sewing away. You know, it's just, we're having an interesting time there getting this ready. And so it's anything but secret. And it's our fifth year of field testing. 1 year was up in Canada with an ice expert there on a provincial park lake. You better believe we were careful about our materials there. This is our 4th year, going into our 4th year testing on this lake. And we just kept going, and we run out of time. Our instrument guys, we had to push everything forward a couple weeks because the freeze was going to happen sooner than we had at first thought. You never know with weather. And so we ended up, it was going to be materials around this nice sensing platform with solar panels. You want to have it out there for the whole season. Ended up putting most of it back in the pump house, floating just a little bit with a camera this time. We'll be back, but as you said, there was schedule. We had to get on with it. And why didn't we deploy it in the dark? Man, these guys are dedicated enough. They would have gone for it. I finally looked at him about 8 p.m., our lone kayaker there who was going to be dragging this out, and I just had to look him in the eye and say, "Do you feel safe doing this?" And he goes, "No." Okay, end of story. So that's the level of caution that we're going to. But what does it cost? Because if this thing's going to cost $1 million a square foot, even if you want to do it, who's going to ever fund it, right? And so looking at various sphere diameters that we have, we're passing around coarser materials than that because I'm only working with coarser materials because I can guarantee I can put them in the bags, I can get them back off the lake. You can end up getting, from this particular vendor, you can end up getting cost coverages of 1 cent per meter squared. That's friendly for the teeniest ones, or maybe 20 cents per meter square. The most optimistic thing then says maybe $500 million per year of historic ice replacement. That is, the melt that we had in 2000 was about 50,000 square kilometers per year, summer to summer ice disappearance. It's worse now. That's the order of magnitude of just the materials, not deploying it, not any of that. But it's more complicated than that. We've never used particles this small. We might decide that the prudent thing is to contain them when we go ahead and deploy them. And, you know, what am I containing them in now? It's basically much more ambitious forms of this laundry bag, but it's that. And that's not cheap. So there's, and getting the materials there. So there's a lot more expense than that, but that gives you kind of the order of magnitude. It may be, Russell is cautioning me that it may be that as we get to really tiny sizes, they won't be as optically efficient as what we have. You know, there are many things to establish, but this is the trend of what we're doing. And I would say that my plea here would be that experiments like this, you really have to get out there and be allowed to do them without spending your life, you know, in legal battles in order to try to establish whether it will work and go on from there. And so what are the talking points here? We've talked through this is my last slide. Why geoengineering? What are some alternatives? Reversible low impact ways to help may give us some time. ICE 911 is useful for several things, including ice preservation, perhaps permafrost, perhaps even rebuilding ice. A point that I failed to make, I'm glad I'm reminding myself, young ice melts more quickly than old ice because it doesn't have as much air built up in it. Perhaps if these materials get incorporated, this is what we want to find out this winter, get incorporated in the ice as it forms, that ice will not be as likely to melt out the following season. That is a big deal. That could help interrupt the ice albedo feedback effect too. And I think you've seen, we always do small-scale testing. We're transparent. We clean it up. We're doing intentionally and sometimes really irritatingly slow and steady progress because you've got to be cautious in small scale as you're starting. And a huge question is going to be whether we can afford to deploy these uncontained or whether we're going to have to contain them. That's going to drive a lot on costs. And are small sizes acceptable? Optically, are they effective, or do we have to go to larger granules like I'm passing around the room, which ups the cost? So thank you. Thanks a lot.
Russell.
Okay, I think okay, so it's actually on this one. Okay.
It's Kingston.
Yep.
And
What's the name of it? Okay, it's already on.
I'll be able to turn off the timing, and I'll be able to advance by clicking.
Okay, yeah,
Right.
yep.
Thank you.
Good afternoon. My name is Russell Seitz. For the most of my academic career, I've been in and out of Harvard MIT, first in policy analysis at the Center for International Affairs under Sam Huntington, and more recently, I've been fellow of the Department of Physics there. About 25 years ago, I was embroiled in one of the first battles of the climate wars, which was the controversy, first really big climate modeling controversy, which was about nuclear winter. And two of the people who were more or less on my side in that were Steve Schneider, who Leslie has mentioned, but also Paul Kreutzen. And Paul Kreutzen, of course, is better known as an atmospheric chemist who, with Molina, took the Nobel a couple of decades ago for pointing out the risk to the ozone layer. Well, in 2006, Paul had become sufficiently concerned about the inability of politics to constrain carbon dioxide growth in the atmosphere that he made took a great personal risk and published the first serious paper on global solar radiation management, proposing to put sulfate aerosols in the stratosphere to emulate the volcanic eruptions that cool the Earth periodically. Well, having known Paul for a long time, talked to him about this, and I said, well, it's a great idea. It's excessively great. It's obviously going to work, and it's obviously ridiculously inexpensive. But being insanely great, this idea of yours has got some insanely wrong things with it. The first is that so far in human history, geoengineering has happened by misadventure on local scales. Over geological and human history, mankind has so far changed the albedo, the reflectivity, of roughly 1/2 of the land surface area of the Earth. Agriculture, hunting and gathering, slash and burn, over 1,000 generations, it adds up to a large amount of real estate. And as we change the color of the landscape, brightening it in some cases, darkening it, certainly, brightening the landscape in some cases, darkening it in others, we create an albedo footprint just as we have a carbon footprint. And the more we individually darken the landscape, the more sunlight the planet absorbs. The problem is the Earth is not very bright to begin with. It looks like a pale blue dot from deep space because what you see is the clouds in the sky. Underneath the cloud cover at the surface, the planet is mostly water and the water is mostly deep. As Bob pointed out, the deep oceans absorb 93% or more of the sunlight falling straight into them. That's literally as dark as an asphalt parking lot. And anybody who's had the experience of walking in bare feet of a summer's day from white sand onto black asphalt knows what that means. There's a temperature difference of about 100 degrees. And the consequence is that we live on a planet largely covered with water, and that water is, to a first approximation, nearly black. So far from being a pale blue dot, we are stuck on a dark blue arc. And the reason the planet is as warm as it is, primarily, is because of its low albedo. On top of that comes the problem of man-made climate change resulting from what we put into the atmosphere. But unless we think about the Earth we're standing on, or the water we're swimming in, we're not going to get a very serious handle on the problem. Now, the corollary to water being very dark and easily warmed by the heat of the sun is the fact that the more you warm water, the faster it evaporates. And from this arises a more acute problem than climate change. Climate change is happening as fast as it happens. And at present, that is a matter of tenths of a degree per decade at most. We are worried about the acceleration of that rate to yield multiple degree changes in the century to come. But in praxis, more people are suffering from lack of water than from the acute effects of long-term temperature change. So in terms of the human condition, there is more of a water crisis than there is, in fact, a climate crisis. But strangely, not terribly much has changed in water management besides storing a lot of it over the course of the Industrial Revolution. We still leave water exposed to the elements. It evaporates because the sun beats down and warms it, and the wind blows and evaporates it. In consequence of this, we face a problem because we don't know how to economically save water from evaporating, because simply we don't pay enough for the water. It's too cheap to conserve. And in consequence of this, the world is currently losing per capita. For everyone in this room lost a ton of water yesterday to solar evaporation. That's stored fresh water, not seawater. And the sum of all of this loss from reservoirs and agricultural canals and in the fields is on the order of $10 billion a month. This is a macroeconomic problem. So we have what amounts to a paradox. The whole hydrosphere is left to evaporate absent engineering or geoengineering. And in consequence, we're letting this happen even though we've already done a lot to the landscape. And some of the things we've done to the landscape have not been local, they have been regional. The good Dr. Franklin of $100 bill fame warned us in 1751 that us Americans were changing the albedo of the earth. We are, as I may call it, scouring our planet by clearing America of woods and so making this side of our globe reflect a brighter light. Now, that's the upside. The downside is, of course, that the modest improvement in the brightness of the American landscape was purchased at the cost of gross deforestation and putting a lot of carbon into the atmosphere by decay. So, nonetheless, the fact remains, geoengineering is part of the human condition and has been since the invention of fire. The question, as Stuart Brand famously pointed out on the cover of the Whole Earth catalog, is what do we do to get good at it instead of simply letting it happen by misadventure? Well, the problem is that in the case of water conservation, is that when water is only worth $50 an acre foot, which is the going rate in the western United States, $300 in rare cases, $20 in others, at that price of $50 an acre foot, you only get about 1 cent per square meter of economically valid subsidy for saving the water. And it's very hard to cover anything with anything for $50 an acre. The skimpiest plastic scrim used to keep the moisture on tomato fields costs on the order of 7 cents a square meter, or about $300 an acre. That obviously is not going to pay to put over a reservoir, even if it lasted, which it wouldn't. It's a fragile disposable material. More substantial materials, as Leslie knows, tend to weigh more. And eventually you get to the conclusion that if you want to be able to enable the poorest people on Earth to save the little water they've got, the cost per square hectares per acre has to be nearly zero. Unfortunately, it's very hard when you first look at this to think of physical materials with which you can cover water that cost less than the water itself. And so this problem was pushed into the too hard pile by analysts for generation. And it is only because of Kreutzmann's pointing out the unreasonable mathematical power of dividing things into small pieces, aerosols in one case, hydrosols in the case I'll be discussing, that you realize it's a hard problem, but it's not impossible because air is cheaper than water. And if you can use air to modulate the optical properties of water, you can change its rate of evaporation and how much solar heat it contributes to the Earth's climate. Well, the trick, very simply put, is that if you take a look at out of doors this time of year, in Washington certainly, you'll see water in all its forms. You'll see snow over in the highlands of Virginia. You'll see water clouds in the sky and dark water in the Potomac. It's all the same material. How come it looks so different? Well, the answer is there's a difference between reflectivity and color. Water is dark in thickness because it has an absorption spectrum. But if you put a bubble of air in water, you get refractive index contrast and it scatters the light. In some cases can reflect it. Well, my epiphany, having talked to Paul a lot about the aerosols, was that there's a strange symmetry, which is that since clouds are nothing but small drops of water hanging around the sky reflecting a lot of light and being white, well, it's just water and air. What happened if you reverse the roles of the air and the water, and instead of having a lot of droplets of air, a lot of droplets of water hanging in the air, you have a lot of bubbles in the water? The answer is nothing much. It's the same thing optically, and that even though you can walk through a fog bank and barely see the droplets, it still is very bright. Well, by corollary, if you make an underwater fog of these bubbles too small to rise very fast, you can make objects, we call them hydrosols, that are just as bright as the clouds in the sky. And consisting of air and water are composed of materials that are no more expensive. The process is pretty simple. The easiest way, the one we're practicing, is to take water and supersaturate it with air at very modest air pressures, like bicycle pump pressures, 4 atmospheres. The pressure in your car tires will essentially double the amount of air that dissolves in the water. If you release the pressure under the right conditions, which is a swirling flow nozzle, the water could no longer dissolve that much air, and shazam, you get a large number of microbubbles. And this is where the mathematics comes into serious play. 1 cubic centimeter of air, a quarter of a teaspoon of air, can obviously fill a 1 centimeter bubble, which can reflect light from 1 square centimeter of its shiny surface. If I take that same cc of air and I divide it into 1 micron bubbles, I have a million of them. So, it beggars the imagination of Carl Sagan. You get 1 trillion bubbles from 1 cc of air in a process that is energetically and not very demanding, and technologically not very complex. As Bob has pointed out, this leads to the conclusion that there is a way to address the brightness of the Earth's surface and its interaction with solar radiation that is pretty much equivalent in terms of the radiative balance to the White Roofs project that Steve Chu has started. The difference is that whereas the supply of roof is very limited, the hydrosphere is almost as big as the atmosphere. There's 300 million square kilometers of water and change on the planet. There's no lack of water to brighten, although there's a very limited supply of roofs and roads. Also, the water tends to flow downhill and gather in one place very conveniently. If you try to get 10,000 building permits out of Mayor Bloomberg City Hall, you're going to make a lot of lawyers very happy, but you aren't going to do much about global climate change. For the same money, you could possibly actually improve the aesthetics of Central Park, the pond in which is 1,140,000 square meters. It's equal to every roof on the Upper East Side and the West Side. So the question of dealing with urban microclimates by brightening water as well as roofs is an open one. I think the economics there are pretty attractive. Now, the objection to Creutzon's great project is that geoengineering is by definition global. And when you moderate the summer weather in the northern hemisphere by dimming the sun, you automatically make it colder in the southern winter, because that's the nature of the globe. We have two seasons at one time, like it or not. So you need some degree of control over what you're doing in area. And this is my slight elaboration on Bob's slide. The stratospheric aerosols offer poor latitude control. On a good day, David Keith hopes they can get a band of aerosol clouds concentrated within 30 degrees north and south of the latitude of injection. They have no control over latitude. 6 weeks later, the stuff's all over the planet, courtesy of the Bailey cell circulation and goes over the intertropical convergence. Now, Messrs. Latham and Salter have a more modest proposal, which is to use a fleet of ships to squirt aerosols from the sea into the marine boundary layer to increase the number of halite crystals that nucleate water droplets and increase the aerial coverage of marine clouds. That gives you good control over latitude. You know where the ships are. And because of the windage, what they release blows downwind, so they have fair control over longitude. And instead of being unable to turn it on and off faster than months, which is the case for the stratospheric aerosols, they can do it in a matter of days. Well, most of the polemic extremity in the climate wars arises from the fact that people don't like to be pushed around on either side of the political spectrum. And when people talk about controlling the Earth's climate, everybody complains because they all have their own climate. All climate is local as experienced in terms of the human condition. And if you can't control whatever you're trying to do in terms of a day's drive or so from the constituency that gets to say yay or nay about whether it should or could or will be done, then you're asking for trouble or proposing to implement tyranny, depending on your political druthers. Whereas the problem with aerosol geoengineering or solar radiation management is that there's no control. It becomes global by default. My problem is I don't know how to make hydrosols last long enough to spread over areas of 1,000 square kilometers, let alone 1 million or 10 million. We have to work very hard to make the microbubbles not disappear in a matter of seconds or minutes. And that provides an automatic off switch. Bubbles are ephemeral. They're less ephemeral in natural waters than in pure water. because the real world is a place where water has stuff dissolved in it. A long time ago, a great American philosopher by the name of W.C. Fields remarked in a motion picture when offered a glass of water, "I never touch the stuff. Fish swim in it." Well, they do a lot more than swim. And marine waters, seawater contains on the order of 30 million nanoparticles per cubic centimeter in the state of nature. And the oceans at large contain on the order of 30,000 microbubbles of 10 micron dimensions, simply as an artifact of whitecaps and wave breaking. The equilibrium state of the sea is to have a lot of air, forced into its surface by wave action. Now, these bubbles are vastly larger than the microbubbles you can make by design, which have a volume literally 1,000,000 times smaller than the marine microbubbles, and which therefore give you a vast amount of leverage on energy. However, the marine bubbles have a lifetime that varies all the way from tens of seconds to tens of hours. And this is because the small amount of organic matter dissolved in the water from algae and such has surfactant properties. And the air-water interface, the sea surface, is naturally covered what's called a pneumonuestron, a thin layer of goo arising from the floating up of all the organic debris from below. It ends up as sea foam on the beach after a big storm like last week's. Well, that Gelbstoff, that small amount of dissolved matter, radically alters the dynamics and the lifetime of air bubbles. Instead of dissolving in milliseconds or seconds, as is the case in purified water in a clean room with no particles in the water, real-world bubbles in Cambridge tap water, unfiltered, last for about 3 minutes, as I showed you earlier. And if you purposefully spike the water with more of the same, algin from seaweed or lecithin from soybeans, you can up the lifetime to on the order of 45 minutes very easily. Very little work has been done to see how much longer you can make bubbles last, or how and what are the parameters that will optimize the bubble lifetime in terms of what you start with. Now, the water conservation prospects vary enormously, as do the bubble lifetimes. People don't cover canals, which are a very obvious place to save water in transit, where evaporation is high because the water moves, because putting a roof over the canal will set you back hundreds of $1,000s per acre of surface covered. It's architecture. When you get down to floating textiles strong enough to last through a whole season in a storm, they're very expensive too. Even snowmaking, which uses just air and water, is energetically almost prohibitive. The various things you can cover snow and water with, likewise, at the margin, tend at the very least, as Leslie's pointed out in her slide, to weigh tens or hundreds of grams per square meter, at which level they will weigh hundreds of kilograms to tens of tons per hectare. It's a lot of stuff. Well, the only two ways I know as a physicist of avoiding that are either to use something that doesn't weigh anything, or to use something that's of ordinary density, but to use it in ridiculously small pieces. Paradoxically, the smaller you make bubbles or spheres, the more powerful their capacity to scatter light becomes. So here for show and tell is approximately, let me see here, 10 to 16. Here's a million billion 1 micron silica spheres packed in a lattice to give you an idea of how bright small things can be. That number of microspheres could, in theory, brighten about 100 tons of water if you were an Alka-Seltzer tablet. We don't know how to do that, but we'd like to do some research on finding out how. The the efficiency that can be achieved using these bubbles has been subject to a fairly elaborate program of modeling, using models devised by NASA and elaborated by people who use satellites for finding things, into a three-dimensional model of what's called scattering that leads to the following conclusion. The natural ocean microbubbles only add up to an area of roughly 1 centimeter per square meter of surface area in the ocean. So their impact, and they're large, not efficient as scatterers, so their impact on the reflectivity of the Earth is quite small. But small as it still is interesting because the ocean microbubbles, which account for only a part per billion or 5 parts per billion of the volume of the ocean, are responsible for, roughly speaking, 1/5000th of the reflectivity of the entire Earth. And if you make them smaller, you can amplify that. And this is what you get in the model that we published in Climatic Change last year. Roughly speaking, if you take if you make bubbles that have through their lifetime an average diameter of a micron, while they're around, it only takes 1 part per million of them to double the albedo, the reflectivity of water. Admittedly, it's not much to double. But you could also triple or quadruple it and still not get to 10 parts per million volume of air. 10 parts per million air by volume is less than a part per billion by weight. And air is very reasonably priced. It is the energetics, not the materials costs, that will enter into the economic debate. Now, a lot has been done to extend the lifetime of microbubbles because people have paid to have the research done. Vast sums have been invested into making ice cream and paint cheaper and worse by adding air bubbles to them to exploit the fact that the air is free. So the food chemists, including some at Harvard, have actually gotten microbubbles in ice cream to last for what years? 5 years so far. Not much hope of their disappearing anytime soon. So you can now get ice cream with a shelf life of, that doesn't crystallize in your freezer until you discover it next year and throw it out. The same is true of paint. Instead of putting $1,000 a ton titanium white in the paint as they used to, they cut it with air bubbles, which don't do such a great job, but which are seriously cheap. Now, the natural surfactants that make some seawater bubbles last for amazingly long times seem mostly to derive from algae. There's also a physical process of bubble stabilization caused by the nanoparticles getting embedded in what are essentially Langmuir-Blodgett films, 1 molecule thick films with the air-water interface. Even at 1 molecule thickness, having an oily substance or an algal lipid or gelatin at the air-water interface will slow the gas diffusion by roughly 2 or 3 orders of magnitude. So there is hope that R&D can make bubbles last controllably for periods certainly on the order of large fractions of an hour. That's been demonstrated, possibly for many hours. When you get to days, you start to blur the distinction between thin liquid films and solid spheres. Glass microspheres are a limiting case of a bubble that doesn't go away. The organisms that make the surfactants grow in the ocean, the variability obviously has something to do, variability in lifetime has something to do with the amount of life in the water. And marine biology could presumably inform us, if they were funded, to tell us what exactly is responsible for bubble lifetime, and then you could talk about promoting the organisms that make bubbles last longer. And the final thing that arises, one of many serious objections to this scheme, is it does not address ocean acidification in the sense that it will not reduce the uptake of CO2 by the ocean. If anything, it would very slightly promote it along with dissolving more oxygen, just because cooler water dissolves more gas. However, the impacts of acidification, coral death, for example, are temperature related as well as water chemistry related, simply because if you take the seawater that's bothering the coral and the Great Barrier Reef, the hotter the water it is, the lower the calcite compensation and the greater the acidity stress on the coral. Cooling the water off helps. That is not intended to be a justification for the enterprise, but simply to point out that for every systems biologist who would like to put the kibosh on such research, there is a coral conservationist who wants to try it out by shading some coral, his favorite patch of coral, with microbubbles that would both cut down on the UV flux and cool the water. The sea ice question is paramount, as Leslie's pointed out, simply because the albedo loop in the Arctic is both amplified by the geometric optics of the atmosphere. The optical depth of CO2 is highest at the high latitudes, and by the fact that there is such a conspicuous link between how much white there is in the Arctic and how cool or warm the planet gets. I must take issue with Bob, who said that we were thinking about sailing around the Greenland fjords around Greenland to keep the ice cap on top of Greenland type of ice cap. No, it would be nice to cut glacier advance due to underplating and undercutting by cooling the water in the fjords. But the real issue is the free sea ice around the North Pole, the Arctic ice floating in the water. That's what's receding, not at 50,000 square kilometers a year, as Leslie said, but this last year at over 1 million reduction in the ice minimum this last September.
It's accelerating a lot.
Yeah. So the areas involved are therefore, the area at risk is millions of square kilometers. But as Bob points out, there's an interesting geometric point, which is that we are talking about when you get to systems that can be controlled to less than a degree of latitude, that are actually local in the way you deploy them. You can do things that instead of being three-dimensional all around the globe or hemispheric are actually local. That you could take a boatload of whatever medium could brighten the water and lower the temperature and not brighten the ocean, and we're not going to make suds out of anything, these bubbles don't rise, but simply paint the ocean a brighter shade of blue at the edge of the ice in the band possibly 1 kilometer or 10 kilometers wide. The ice margin is roughly speaking 10,000 kilometers up there in the Arctic. So the area that you would have to cool to reduce the recession of the ice is probably on the order of 100,000 square kilometers or less. The area of the ocean is 300 million. We are talking about tenths of 1% of the area of the oceans, not about global engineering of the hydrosphere.
Russell, I think we're going to have to move on to the next presentation.
Okay, just to conclude, this is a generic proposal in the sense that there are already small-scale applications like cooling ponds, which when they get hot shut down power plants or make them run less efficiently, leading to excess consumption of fuel and emission of CO2. The misconceptions that I want to kill at the inception are that we are out to darken the depths and kill the plankton. We're talking about materials that scatter light as well as reflect it. They change the shape of the euphotic zone more than they actually reduce the flux. Every time we have a cloudy day, the solar flux in the ocean goes down by 20 or 40 or 60 or whatever number of percent. It's that order of magnitude, and you can turn it off at night. We're not going to turn anything into a bubble bath because microbubbles don't rise in the first place. We're going to create underwater clouds, not suds on the surface. Lastly, this will somehow change the ocean chemistry or do something unknown to the ozone layer. Wrong discipline. This is a category error. We're talking about physics, not atmospheric chemistry. And surface cooling can, in fact, increase the available oxygen by making the water cooler. So there are risks in abundance, but the bottom line is that the greatest moral risk may be that of ignoring our own albedo footprint. We have one, we'd better learn to manage it well.
I'll take care. Thank you.
Thank you.
Thanks, Russell. Jim. Oh, yeah.
No, it's okay.
Oh, which, okay. Yes.
Thank you very much, Russell and Leslie, and Bob as well. And thanks very much to the Wilson Center for inviting us to have this very important discussion. I should say a little about who I am. So my name's Jim Thomas. I work with an organization, a non-governmental organization called Etc. Group. We're a very small international group. We're a kind of a watchdog group for emerging technologies. I think we're sort of a sort of scrappier version of the STIP program in a way, but you know, rather than the sort of elegant discussions you have here in corridors in Washington, we have discussions often with civil society partners, with social movements, with farmers, with indigenous people. We also tend to work more at the United Nations, at the Convention on Biological Diversity, the Food and Agriculture Organization, and other places like that. But it's important to have this discussion here in Washington, because in our view, in what we're noticing, having been watching geoengineering for maybe about 6 or 7 years now, is that there is a push coming out of Washington for some of these schemes, whether soft or hard. I'm going to start by pushing back a little bit on the language of soft geoengineering. I have to say I really enjoyed the first report that you did, Bob. It was extremely subtle and nuanced and useful. I'm less happy with this report, and partly it's this language of soft geoengineering. And so I'm just going to unpack that a little bit, and we'll hopefully have a bit of a discussion around that. So when I saw this language, soft geoengineering, I was trying to understand why would you use that? Why would you talk about something as soft? You know, usually it's pointing towards that there's something wrong with the normal version. You know, like you know, it's when people talk about soft war or soft torture, soft rape. That this language of modifying something as being soft, so that as to make it more acceptable somehow. You know, the danger is it masks something that is fundamentally problematic, and certainly that's how we see the notion of geoengineering. Maybe it's soft drugs. Maybe we're talking about gateway geoengineering here. You know, why would you use this language of calling this soft? I'd suggest a different term, and we should call it soft cell geoengineering. What we're talking about here is trying to differentiate types of hard or soft geoengineering such that we can get people comfortable with the idea of geoengineering the planet, which is a repugnant idea, and I think we shouldn't forget that at core it's actually a very worrying, and I don't know how you put it, but I think you said rather scary idea. We shouldn't get too desensitized to that, and we need to make sure that talking about soft geoengineering doesn't desensitize us. I was surprised in the paper and in your presentation, but you explained this to me earlier, that Bob didn't say where the term originally came from. Soft geoengineering first emerged in an article in 2009 that was authored by Samuel Thernstrom. So Samuel is one of two people who runs the geoengineering project here in Washington at the American Enterprise Institute. And some of you may be familiar with the American Enterprise Institute. And they're interested in geoengineering, and we'll talk about this in a minute, along with other more conservative think tanks who in the past have said that there was no such thing as climate change, and now saying, well, if there is, we can always geoengineer. Here's what Samuel said when he first used that term. He said, soft geoengineering techniques, and he said in the article, they're probably not very effective, but they are less ambitious, less disruptive, less threatening, and so they're important because they get people used to the basic concepts of geoengineering without scaring them. And in so doing, they expand the scope of climate policy discussion in important ways. I would say that expanding the scope of climate policy discussion to include geoengineering is a very dangerous way to go, and that's partly what I'm going to be suggesting here. I kind of want to make 3 points in my presentation about why we should be worried about trying to hive off soft geoengineering and somehow embrace it. The first is, it ain't all plan B. So the presentation that you heard from Bob, and it's true, is that for some scientists, like Paul Crutzen, the reason why there's an interest in geoengineering is because we may need it. We may be reaching a point already past a point where climate change is so bad that we have to reach for this plan B. And that's certainly a valid reason to have the discussion. However, I think that the reason why the discussion is coming up, particularly here in Washington, and particularly from some of the countries that have been least active in acting on climate change, is because you have a number of people who see it as a potential plan A. And that's really what's driving this discussion right now. So Newt Gingrich of, in fact, the American Enterprise Institute, back in 2008, sent out about 20,000 leaflets that said, "Stop the green pig." It was against the Boxer-Warner-Lieberman bill. And saying very clearly that we don't need to do all these actions to reduce emissions and put in place a carbon market and so forth. In fact, we can use geoengineering and it will be much cheaper. There's one method that holds the promise of addressing any threat from global warming at a fraction of the cost. And instead of penalizing ordinary Americans, we'll have the option to address global warming by rewarding scientific innovation. This argument, which in fact was repeated just last week, I think, in the Wall Street Journal by somebody from the Manhattan Institute, is an argument we're hearing again and again from what I call the Plan A crowd. And many of them are here in DC. It's not just the American Enterprise Institute and the Heartland Institute, who you may know convenes the annual Deniers Conference, the Jefferson Institute, the Cato Institute. Bjorn Lomborg, somebody who previously said climate change isn't an issue, now says that geoengineering is the thing we most need to deal with climate change. So we go from, we call it the Lomborg maneuver, going from there's no such thing as climate change to we must take the most extreme possible response. So let's be clear, though, what's driving this discussion isn't just the Plan B concern. There are other agendas at play. And it's not just Plan A. There's Plan C as well, commerce. We do have people who are interested in making money, and this has been touched on a little bit, whether it's carbon credits. So there's Russ George. He's the person who just recently managed to convince a small native community off the west coast of British Columbia to put $2 million into dumping iron in the ocean, claiming that he'd be able to get carbon credits for them. There's never going to be any carbon credits. He misled them. It's quite a tragedy, quite aside from what he's just done to the ocean. Russ George has tried this a few times. He had a company called Planktos where he tried to dump iron west of Galapagos, and then he tried in the Canary Islands. Here's something he said to, so I think it was an NPR program. It's really more of a business experiment than a scientific experiment. And we do have a number of commercial companies. You heard that there were 4 commercial companies interested in air capture. There have been a number of companies interested in ocean fertilization. And some larger players too. Nathan Myhrvold of Intellectual Ventures, formerly Chief Technology Officer with Microsoft, has got patents and is putting significant money into trying to produce, trying to commercialize something he calls the stratoshield, which would be putting sulfates in the atmosphere, but also techniques to try and slow down hurricanes. Richard Branson is putting money into biochar and a number of other things. Also, Bill Gates, as well as putting philanthropic money into geoengineering research, is also investing in some of these companies. So there is, and these are hard-nosed businessmen. They expect some money back, and whether that's going to be through incentivizing through carbon credits, as Russ George thinks, or some other kind of credit system. Russell, it was in the paper from Bob, there was a suggestion that Brightwater could be paid for through kind of carbon credits. Well, there's no carbon being sequestered. You'd have to create a kind of thermal credit. And if we get the development of a sort of a thermal credit for reflection, then we really do have some things to worry about. A whole new market, a speculative market in solar radiation would be, I think, a really dangerous move. But the suggestion's already out there. Or these kind of co-benefits. So, you know, we heard Russ George proposed that he would get money back from increased fish production. And certainly with ocean fertilization, we've heard that. So various ways to monetize geoengineering changes the reason why it's happening and the caution with which it happens. And of course, there's Plan D. It's worth being aware that geoengineering has always been around as a defense suggestion. And in fact, the early proponents of, for example, putting sulfates in the atmosphere, whether that's Lowell Wood over here or Edward Teller, father of the atom bomb, the father of Star Wars, their interest was initially military. And that's still very much in the background. DARPA's putting money into research on geoengineering. There's a lot of interest in local geoengineering particularly, because if you can control local climates, which is what we're just starting to hear a little bit about here, that's a wonderful weapon of war, if you could deploy that. So that's also in the background. So let's kind of be careful that whether it's soft or hard, there are other agendas at play here. I think it's important also to recognize that scale matters a lot. And one of the criteria that you put, Bob, was, well, it can be locally applied. Well, geoengineering isn't local. The point of geoengineering is it's large scale. The point of geoengineering is that when you scale it up, it has a large scale effect. The climate is a global system. And even if you try and work with parts of that, there may be other effects. And I think we've seen this before, where something has been sold as a small, local, soft approach, that when you scale it up, all sorts of scale effects begin to appear that are really quite serious. They're not so soft at all. So biofuels, I think, is the perfect example of this. That, in fact, it was a soft sell back in the 1970s when Amory Lovin's, soft energy paths.
That's where I got it.
That's where we got the language from. Then there are the crops that were going to be turned into biofuels. It's a soft energy path. It's a soft response because it's natural. And for a lot of the environmental movement bought that. And a lot of very well-meaning people bought that. The soft sell. It's better than oil. It's better than gas and nukes and so on. But as we saw, particularly in the last sort of 5 to 10 years, an actual increase in biofuel plantings, especially ethanol, then the effects have been pretty horrific. We're looking at the largest land grab in 300 or 400 years. You're needing biomass, you need good land, and that biomass is all mostly in the tropics. So the people who are getting kicked off of their land are people in sub-Saharan Africa, it's in Latin America, it's in Southeast Asia. 86% of all biomass is in the tropical band. And so we're seeing biomass, these grabs for biomass, people being pushed off their land with all sorts of violent implications there. But we're also seeing that as a climate change response, it's not a very good one. That the change in land use liberates a large amount of carbon dioxide from the soil. That the need to use fertilizers and so forth actually means that you're creating a lot of greenhouse gases, that when you burn biofuels, you're actually releasing more CO2, and that doesn't necessarily all get fixed. It doesn't work at scale. And particularly with ethanol, that's now very clear. And it's going to become more and more clear as people look at the so-called second generation, third generation, fourth generation. It's just not a real fix. And my worry is that something that looked good on a small scale here turned out to kill people, quite literally. You could see the same with local soft geoengineering. And I guess some examples of how once you scale up some of these things that look soft on the small scale, the problems become more apparent. So here's David Keith's large air capture device, which looks soft enough. It's a little bit brutal architecturally, but as Bob pointed out, one of the issues here, of course, is electricity. Is that there's going to be a lot of energy to run that. Where's that electricity going to come from? Well, it could be coal, who knows? But even beyond that, there's a set of other issues. The most commonly discussed absorbent for air capture is sodium hydroxide, which is made through the chloralkali process. It's the same process that makes chlorine. So potentially you're going to end up with a large production of chlorine if you begin to scale this up. Chlorine is a particularly deadly chemical for living systems. So if you're going to have a massive increase in chlorine production, what's that going to do to ecosystems? Where's that chlorine going to go? Is it going to get into people's bodies? That question has to be addressed. The question of what you're going to do with the CO2 So as Bob said, maybe we're going to use it to take more oil out of the ground. Well, clearly that's not a very good climate response. If you're liberating more fossil fuels, then you're leading to burning more CO2. But the idea that's been proposed by companies like Global Thermostat and Kilimanjaro, and also David Keith's Carbon Engineering, is that they'll partner with algae companies. So I think it's Kilimanjaro, Global Thermostat. One of them are partnering with Aurora Algae. Well, algae has a lot of problems too. And the idea of algae biofuels has a lot of problems, which is what they're claiming they'll do. Not only are there issues to do with the genetic engineering of algae, which is what's going to be necessary to sustain biofuel production, and that's become clear. Anyone who watches the algae biofuel sector knows that's where everything is moving to. Aurora is working with Monsanto and others, and mostly using synthetic biology. So that's another thing for the STIP program. But algae doesn't just grow on carbon dioxide. It requires nutrients. So you require fertilizers. And most of the assessments of the life cycle of algae as a biofuel source fall over on this requirement of massive amounts of fertilizer, more than corn, if you're going to be doing them in ponds. And fertilizer, of course, is one of the largest producers of greenhouse gases. So straight away, you can see how this begins to fall down. Where are you going to put your large algae ponds? Probably in deserts. Craig Venter's algae company was looking to do in Peru, in the Peruvian desert. What does that mean for indigenous Peruvian people who would get pushed out the way? We have a land grab issue again, and so on and so on. If you're going to scale this up, you're going to have all of these sort of effects. It might look benign at that size, but at a global size, it's not so benign. Microbubbles, I don't know much about microbubbles. It's been really interesting listening, but I do know that so the UN Convention on Biological Diversity has been dealing with the questions of impacts on biodiversity of geoengineering technologies. They did an expert review of the impact of different geoengineering technologies on biodiversity. Earlier this year it was published, and it was discussed just recently in Hyderabad at the COP11 of the CBD. This is what they say about microbubbles. The feasibility of the scheme at scale required is highly questionable. Again, it's about scale. That once you begin to do so, there will be major biodiversity and biogeochemical implications. Impacts of decreased light penetration, what does that mean for the ocean? Temperature changes on phytoplankton, microbial composition of the sea surface. These sort of things, once you do it at scale, can be very significant. So again, we have to think, when you move up to a scale, this is going to be less soft. And biochar was mentioned, the idea of putting charcoal in soils as an amendment. You have many of the same issues with biochar as we have with biofuels. It's a biomass-based solution. The assessments that are done by the biochar proponents themselves, like Johannes Lehmann, say if they were going to deal with 12% of CO2 emissions and be able to offset 12%, they would require 556 million hectares of fast-growing crops, mostly in the tropics. So we're talking about a land grab question here again. 556 million hectares is roughly the size of the EU. And that's only 12%. So let's imagine nobody would do this, but theoretically you wanted to try and get 100%. You're talking about the size of the Asian and Middle Eastern subcontinent. So that sort of land needs are just unrealistic. And here's why they're unrealistic. So there's been a lot of work looking at where is the biomass that you can use for biofuels. And it's the same questions for biochar. This is a really interesting set of maps that was done by the German Biomass Research Organization. Here are the possible regions where you could get energy crops for biomass. And the darker it is, the more chance there is for growing biomass and for energy use. But here are the regions where there's restriction factors, where, for example, there's protected areas, or areas where the biodiversity is too important and too high, or wetlands, which you shouldn't be going into, and questions about water and the amount of CO2 that's released when you change land use. And when you put those together, that's what you're left with. You're not going to get a lot of cooling of the planet if you turn that into biochar. So these, again, at scale, these don't actually make a lot of sense. And biochar has a lot of other problems. It was suggested in your paper, Bob, that it would be a way of storing soil carbon, but actually the longest term tests that have been done again by the biochar proponents, looking at soil carbon retention in soils, show that there's actually quite a massive loss of soil carbon. And it seems that adding charcoal kind of stimulates bacteria that then kind of eat up all the carbon and release it into the atmosphere. So it might actually have a counter effect on what is expected. A lot of biochar is basically soot. If that gets airborne, and some of it does, that's a very serious greenhouse forcing. What if it darkens soils? We're back to our albedo questions. And even the question of whether it's effective as an amendment, whether it improves soils for crops is really unclear. It depends what you put in your biochar. It depends what levels of different kind of biomass you're using. Some seem to be even quite toxic for crops. So there's no clear answer there. This is, so as I mentioned, the Convention on Biological Diversity has been looking at this question about the impacts on biodiversity, and they're particularly interested in this question of what happens when you scale this up. And just a few weeks ago, the Convention on Biological Diversity published a new decision on geoengineering, which reaffirmed the existing moratorium on geoengineering experiments that's already there. And based on these studies, pointed out there is no single geoengineering approach that meets basic criteria for effectiveness, safety, and affordability, and began to look at what are the gaps, how biodiversity and ecosystem services are affected, what are the impacts on biodiversity, these things that we just don't know, and just the research isn't there. So it's way too early to make any kind of claims that these are particularly soft. They did look at all these examples. I'm not sure if they looked at ICE 911. I have to look at that. Thirdly, so we heard about Rusty George, as he's sometimes known, the so-called rogue geoengineer. I think there's a bit of a misleading thing to say that that's rogue geoengineering and other types of geoengineering isn't so rogue. I think in a very fundamental way, and Naomi Klein says this in that article, geoengineering is rogue. It does something that is quite rogue and destructive, and particularly so when it's solar radiation management, when it's about trying to change the reflective albedo of the planet in different ways. And I think what it does is it destroys, particularly as it gains any kind of prominence in policy discussions, which is what's beginning to happen. It destroys the multilateral processes that we have in place for dealing with climate change. So here's here's a meeting, and I think this was in Bonn, of the UNFCCC. And what's been going on in the UNFCCC process is a very straightforward game. We want to keep temperature rise down to under 2%, and we want to do it by reducing emissions. That's what's being negotiated. There's one variable, effectively, for those negotiations. There's 192, almost 200 countries, and of course, it's already extremely complex. There are bad actors in those negotiations, people who would like to put in loopholes and try and get out of their commitments. But it's a straightforward premise, and it's got two things going for it that I think are extremely important. One, it's based on the notion of historical but differentiated responsibility, which in basic says this affects everyone. Everyone has different responsibility for this, and decisions have to be made in common, because it's true, it's a common climate, we have to deal with it together. And the second is that the problem is emissions. That's the root cause, and let's go to the root cause. Let's not try and deal with lots of different variables. Let's play with the one that really matters. And that's already hard enough. If you try and introduce two more variables, so we try and say, well, okay, we're also going to play with the sunlight. We're going to put more sunlight, less sunlight. Then your negotiations become extremely complex. Because you can imagine a country saying, well, we have a lot of clouds on a Thursday, so we don't really need to reduce our emissions. Or we're making microbubbles in New York, so we don't need to do that either. It becomes a cover, another cover for reducing commitments and stepping back from what are already very weak commitments. And then you have the notion of local geoengineering. The notion that, well, we're just going to deal with this on our own. We're going to deal with it here. We're going to change our climate. We're not going to touch your climate, so you don't have anything to say about it. We don't need to worry about Africa because we're changing the states. That kind of complexity, as anyone who's involved in diplomatic discussions will know, is going to destroy the climate negotiations. You can't deal with that kind of complexity, particularly if you have bad actors. And particularly if those who are pushing this are exactly the actors who have been ducking and diving and trying to avoid and put in loopholes their existing commitments. And interestingly enough, that's just fine for the Plan A crowd. They'd love to see collapsing multilateral talks and a more unilateral approach. And it worries me when I see, for example, David Keith Ken Caldera and others, just a couple of weeks saying, we can do local geoengineering. David Keith was speaking at MIT 2 weeks ago saying, I don't think a UN treaty is what we need here anymore. We just need a kind of agreement between the big players, between China, between the US and the European Union, and that's all that's required. What does that mean for those who are really most affected by climate change? That some coalition of the willing is just going to deliver a response and they're going to have to live with it. That goes away from the idea of differentiated but common responsibility. So my suggestion is, let's not go down this soft sell, hard sell geoengineering. That we should have to look at this in policy terms in the same basket and not separate them. And let's put real hard sell on real solutions, real action on climate change, because if this is basically what we're talking about here is governments saying that they'd rather change the sky or change the ocean and put more bubbles in than ask people to take public transport. Oh, that's ridiculous. There's real actions that can be taken on climate change that will make a difference, and let's talk about that because we can make real change. Thank you.
Excellent.
Okay, I think we've got, 15, 20 minutes for questions. Plenty of stuff to talk about, I think. Why don't you raise your hand? We'll get you a microphone because we are videotaping this. So go all the way to the back. Yeah.
Thank you, Harlan Cohen, International Union for Conservation of Nature. I work mostly on marine issues. Want to thank all of the presenters and wanted to ask if, with respect of bright oceans, bright waters, have you had discussions with marine biologists about the range of effects that could be expected on everything from plankton through fish to whales, noting that, of course, fish provide about 15% of the world's protein, but provide even more to the poor and poorer countries, perhaps even 50%. And with respect of char, I'd just like to point out that mangroves, because of their deep nature of their roots and the way their leaves fall, sequester a tremendous amount of carbon. And have you thought about perhaps looking at preserving and allowing for regrowth of mangrove forests might have an effect equal to or more than you would find from the char experiments? Thank you very much.
I can't speak to the carbon sequestration efficiency of mangroves, but on the first question, the impact on marine and lacustrine photosynthesis has been paramount in my mind since the inception of this. The idea stems from an observation about the inordinate effect of marine natural microbubbles on the Earth's albedo. The modeling that has been conducted so far of the effect has to be considered in the light of what the albedo of water is in the first place. It's only about 7%. Doubling it, increasing the reflectivity of the water surface from 6 or 7% to 12 or 14, obviously reduces the amount of light in below the surface by at least 6 or 7%. But that is within the range of evolutionary response of most plankton because they've co-evolved with cloudy skies. Sunlight goes down not by 6 or 7%, but by 10 or 20 or 30 or 40 every time a cloud passes over or we have a rainy day. And the normative response of organisms is of course, phototropic. They swim up when the light field gets dimmer to the level that they is optimal for them in evolutionary terms. And they swim down when it's too bright for their taste. So you obviously are not going to increase biological productivity by abstracting solar energy from the system. But the actual impact on the marine organisms is a complex function of the biological system. So I can't make a generic answer except to say that that is by far the most demanding and potentially labor-intensive area of research that has come out of the initial publication. It's a question. It's not a question. It's a plenum of questions that need to be answered. But I do observe that fish do not drown on stormy days when there are a lot of bubbles in the water, and that long periods of cloud or winters or nights, for that matter, do not lead to wholesale die-offs of the organisms. Whitewater and marine life have co-evolved for several billion years.
I'd like to also speak to another aspect of that, and that's with respect to ice. When ice disappears, you've obviously changed the brightness, the albedo, substantially. And if you're trying to regrow ice and put ice back in place, you've actually returned it more to the situation that things have evolved with, more to the situation the ecosystem is used
Do you
to.
want to say something?
Yeah, I just, while it's interesting to see what naturally occurs in terms of cloudy days and increased storms, we have to be careful not to fall into the mistake that an artificial bubble cloud or so on is identical to a natural bubble cloud. It may be, but certainly the history of looking at ocean fertilization, where it was assumed that fertilizing the oceans would create a plankton bloom that would be equivalent to a natural plankton bloom, has shown very much that actually they're very different. An artificial plankton bloom is quite different from a natural plankton bloom and has very different ecological effects. So we can't naturally just automatically extrapolate one from the other. That needs to be checked.
Yeah, right here, up in front.
Identify ourselves, or?
Sure.
Okay, I'm Helen Rafeld with Resources for the Future. I realize that if you cover the ice with something reflective, you're not changing the amount of reflection, essentially, or very little going back, because the ice itself is very reflective. But as far as the microbubbles are concerned, a cloud up in the atmosphere reflects heat back up out into space. But if you're down at sea level with the microbubbles, aren't you warming the air in the lower atmosphere on its way up? And with the wind blowing, perhaps you're accelerating the horrifying melting of the Himalayan and glaciers that are causing more of the water that we depend on, the freshwater streams, to flow faster and perhaps give us freshwater shortages faster than you would without the microbubbles at the sea level.
Ma'am, would you expect that response to result from painting your roof white?
Yes, I suppose so.
Well, the effect on the air temperature of reflecting visible light in the absence of clouds out of the water is for, roughly speaking, 30 or 40% of it to radiate directly back out into space. It's not heating anything. The absorption of the air is around 10 microns in the thermal infrared. The ocean sea surface does not radiate the way the sun does.
But it's not just... Well, okay, I accept your answer.
Okay. Yep.
Thank you. I'm John McCormick with the Institute for Multi-Track Diplomacy. Before I ask the question, I want to applaud you, Jim, your presentation, and I do hope the Obama transition team will give you a call.
That's good.
I want to direct my question to food availability, because we're really talking about climate change, and geoengineering is a subset of that. And we've already seen the collapse of the world's grain basket because of perpetual drought now, which some appear could be perpetual. Should we also be talking about some kind of another phrase of engineering that would assure that the North American grain basket will have adequate water during the critical times of planting, even if that means tapping into the Great Lakes? But it certainly means revising our entire agriculture base so that we're talking about drip irrigation, we're talking about entirely new crops to be grown at certain times. In other words, adaptation to climate change. For me, the number one concern is food availability. Sea level rise later on, but in the next 2 or 3 years, perhaps we might see some very serious food shortages around the world.
One of the points of ICE 911 is the fact that as ice is disappearing, all the historic weather patterns we're used to change. So I foresee more problems like this unless we somehow get a handle on it. I think you're right. This is an incredibly important area to look at.
The water question is paramount, and one of the people who's been of great assistance to all of us is the former Energy Commissioner of California, Arthur Rosenfeld. And in his experience in that office, he got mighty tired of paying $250 million a year to buy electricity from coal-fired plants in large part, to power pumps to pump water over the Tehachapi Pass from wherever, in order to watch it evaporate on its way down the 100 miles or more of the California Agricultural Canal. The loss of water by evaporation in agriculture ought to be a scandal in human terms. It kills a lot of people by famine annually, and devastates many agricultural economies and destabilizes some. The relative disparity between the complexity of open ecosystems, which require these enormous investments in intellectual work to understand impacts such as the changes in the light field, contrasts starkly with water that's already been harnessed for human use in reservoirs, in canals, in ponds, billabongs, tanks, catchments, on all scales from a 1 acre pond in Uttar Pradesh to Lake Mead. Letting this water evaporate by the ravages of sun and wind is not just a macroeconomic problem, it's a human tragedy. If you can brighten the water by a factor twofold, parts per million of microbubbles, we're talking about not tap water, but water in the water system, not in the state of nature, not in the open ecology. If you double it, you can typically, as I showed in that modeling, you can expect the evaporation rate to go down on the order of 1 millimeter a day, depending on the weather. 1 centimeter in the case of the high deserts, where like Lake Mead, which evaporates 4 meters a year. The amount of water that would be saved in transit would be whole percent or even as much as 10% in some cases. And that could be the difference between feast and famine in many rural ecologies.
Jim, you want? No.
Rain-fed farming, and not so much. I'm sorry. I was really thinking about the rain-fed corn crops in Iowa, etc. Those are the concerns that I had. Not
the problem. So, I mean, I would absolutely agree that one of the reasons we should be most concerned about climate change is the impact on food security and food sovereignty, and the problem there is partly about the changes in the climate, which increase vulnerability and loss of crops and so on, but it's as much to do with the agricultural system, which it's affecting, which is a large-scale monoculture, very inefficient system that doesn't even feed people. It mostly feeds cattle, all of this. And that, farmers historically, and by farmers I mean the farmers who really feed most people, which are peasant farmers around the world, are very good at dealing with changes in climate. They hedge against it all the time. They have complex systems that deal with drought and so on. But to be able to, and they adapt and innovate, and they're adapting and innovating now in locally specific and complex ways all the time. But in order to be able to do that, they need to have a control over their own seed, control over their own land, able to use locally adaptive, whether it's water management techniques or whatever. And that requires a change in agricultural policy. We have farming methods that will retain more soil and water in the soil. Organic agriculture does that to some extent, but locally adapted, people are very good at doing that. The problem, and this is to go back to geoengineering, one of the problems I see with geoengineering is it's an attempt to create a one-size-fits-all solution. We're gonna try and take one big one-size-fits-all answer in terms of innovation, rather than lots of different locally adapted, innovative, bottom-up approaches. And the problem with one size fits all, whether it's in agriculture or climate response, is, it's like T-shirts. It's good for the big guys, but for the small guys, they get swamped by them. And that's the problem here, I think. I would say that what you need is significant change in our agriculture policy, which people like Michael Pollan have been saying for a long time. The food movement in the US has been saying that for a long time. And that can address water retention amongst a lot of other issues. So
we can only do one more question. I'll do Eric back here. People can certainly stay around and talk.
Thanks so much. Eric Hoffman with Friends of the Earth. Jim and Bob both mentioned that really one of the big problems is scaling up, that these ideas can sound good on paper, but when you scale up, you run into economic problems, but more seriously, ecological problems. I was wondering if Leslie and Russell could respond. Do you see your technologies as being scalable? Do you predict that they will actually have an impact on global temperature? Because that's really what we're talking about at the end of the day. And when you scale up, what are the other ecological and maybe even socioeconomic impacts that Jim has raised that might arise from your technologies as well?
So I'll try to address that. Certainly, you could probably tell from the presentation, I believe slow and cautious is the way to go on any of this. One of the slides that's in my backup materials, but I don't think we have time to dig for it, is just a beautiful snapshot somebody painted once of the undersea ice ecology. And that's something I think that's pretty critical to keep in mind while you're deploying things. If we're successful in what we're trying to do, what we're basically doing is rebuilding ice with a, very, very tiny amount of material that's helped for that ice to reform. So it's as low impact in weight and impact as you can possibly have. That's the attempt. As you scale up, the sorts of things that I keep in mind for the math are, what's the energy cost of the sort of materials that we're putting out there? What's the energy cost of getting them there? How hard is it to pull it back if we need to, or do we just reverse the effects by then doing some further thing of darkening again? So those are the kinds of considerations that certainly preoccupy me. I couldn't agree with you more that if you're starting to scale up, you need to do it cautiously. On the other hand, we have this ferocious problem going on. And that is that whether we're taking our time here, while we're taking our time, the ice seems to be accelerating in its melt. And that's a really important and critical balance that I'm keeping in mind. It literally keeps me awake at night. I'm not sure what the right answer is. I do think that it's critical that we continue to do research to have these options available should we need them. But I think even when we get, and I guess I'm concluding there's going to be a when, to the climate emergency that says, well, we've got to make some decisions, and they'd better be made by people other than myself. Do we need to deploy this? That we've done enough background that we understand what those impacts are. Are we better off putting something in place than if we had not? It's going to be critical.
I think Russell is looking for a slide here, so let me stick a reaction in myself while he does that. I very much agree that scaling up things can produce new problems, and so it has to be done gradually. It has to be looked at. It has to be researched. I also agree with most of what Jim said. In fact, I wanted Jim to be here. I asked that he be here. He's very right about the dangers of Plan A, and the people who originally opposed the whole idea of climate change who are now jumping to geoengineering. That's absolutely right. I think he's right about Plan C, B, and D too. Where I disagree is that I think Jim is being too absolutist. I think you have to take these things on their individual merits, and you may find that some of them can be scaled up without creating significant problems. I was talking to somebody who was at a Greenpeace meeting in New York last month, and Jim Hansen, the NASA climate scientist, was there. And Hansen was saying, the most important thing that we just must do is we've got to stop the melting of the ice, because the melting of the ice triggers these self-amplifying effects in nature. And he said, I've come reluctantly to the conclusion that among the emergency response measures we have to take is going to be some geoengineering. And the Greenpeace people were very silent.
Okay.
The danger is that an absolutist approach that might rule out something that could be useful could result in this problem getting out of control.
Yeah, just go ahead, Bill.
Bill Mitz, I'm working with Russell, and I'm also involved in a company called Oceana Energy. I'd like to add to what Bob has just said, a contextual point, which isn't a total answer to Jim, but I think is an important counter. We're beyond the point where even if we did all of the mitigation things that he has proposed and that I believe in, including I would be delighted if we got away from animal protein. I would be delighted if we lived in green cities with modular architecture. I would be delighted if we had an entirely different transportation system. I would be delighted if we all lived like St. Ambrose to some degree. None of that's likely to happen very quickly, unfortunately. And we're at a stage where a significant amount of adaptation is going to have to take place, even with the best efforts with goodwill we do on mitigation. For example, southern Florida eventually is going to have to be evacuated, even if we do all the virtuous things that Jim and I would like. New York City is either going to have to build a huge barrier or begin to move people out of very vulnerable areas, and it goes on and on and on. It is in the context of the costs of those rather massive interventions in our current way of living that I think some of these approaches have to be judged. We're going to have to do some uncomfortable things, even if we're very, very virtuous. And therefore, I think it's only fair to judge some of these so-called softer technologies in that broader context of the need for fairly massive adaptation.
Can I just respond? Mm-hmm. I mean, yes and no. I worry when I hear something, particularly around climate change, that says we are going to have this and we are going to have to do something and we are going to be affected, because it's never clear who the we is. Who's most affected by climate change are the people who didn't really create it. It's populations in the south, it's populations in some of the poorest and most vulnerable countries. That's the we who's most affected. The we who hasn't done anything yet is our politicians. The we who has mostly caused the problems, I would say, is not the general we who are, having solar panels. It's oil companies. It's large scale deforestation. It's some very specific large actors with a lot of money who are working very hard to prevent action from happening. And if there was political will, you could stop them. But there isn't political will. That's the problem. There's no political will in the system.
Even if you stop them?
No, I think you could. And I particularly think that you've got about up to potentially as much as 60%, just under, of carbon emissions are coming from industrial agriculture. But in fact, industrial agriculture isn't feeding anyone. 71% of all food comes from peasant agriculture. You've got a massive amount of carbon that could be taken out of the system if you had political will to deal with the likes of Cargill, Monsanto, and so on. The problem is you need to have political will to deal with those bad actors. And that's where the focus should be, not political will to implement large, risky geoengineering schemes. We need to shift that political calculus, and it can happen. That's why I showed Martin Luther King. You can have that kind of change.
Okay, I'm going to, because we've run over time, take the formal part of the meeting and close it down. Well, I want to thank everyone for coming. I said this is the first of hopefully more post-election discussions that we need to have. There's a lot of hanging questions that have been left. Welcome to stay around and talk to all the folks here if you got more questions. And you're on our mailing list now, I think. So we'll be glad to tell you, when we're going to have the next meeting.
And whoever has the shiny block of microsphere plastic, could they please return it to me?
Thank you very much. Thanks for all the people that participated and talked. It's great. Thank you.
Thank you.